All right, so today's stream, the main part of today's conversation, this will be the last one that we do on nuclear energy. We're going to be talking about what else you can do with nuclear energy besides making electricity. So if we look at what's shown here is the energy flow chart for 2019. It was 100.2 quads. A quad is a quadrillion BTU, which is a British thermal unit, which only the Americans use and someone else like that. The uses that we have for the energy in our sector, it basically goes into four main categories. Residential use, commercial use, this would be like office buildings and stuff like that. Industrial use, which is manufacturing and things like that. And then transportation, which is getting everything around. So this is for the United States of America. Again, this is the Lawrence Livermore National Laboratory Energy Flow Chart. They do this for most countries in the world and states and things like that. They have a few other things like water flow chart, and there's a variety of flow charts that they have. There's a carbon flow chart, although the carbon flow chart only does expenditures. It doesn't do the carbon that goes into generating these different things. And so we can see from this plot that roughly a third of the energy in the United States goes into transportation, about a third goes into the industrial sector, and about a third goes into the sum of commercial and residential use. It's not exactly that. Transportation is the largest, industrial is the second largest, and then commercial and residential is the third largest when combined. But it's roughly a third, a third, and a third. And then these are all the sources for energy that go into this. So you have solar on the top, nuclear, hydro, and stuff. And those all, nuclear, hydro, and wind and solar, that all goes through the electric grid. So you have all these inputs that come into the electricity generation, and then electricity is distributed around. And then you also have, for example, the direct use of natural gas that goes into homes for water heaters and for, what else do you do? Furnaces and stovetops and things like that. So roughly half of the energy that we consume in our homes comes through natural gas, and roughly half comes from electricity. So you can see it's like 5.18 goes into the homes from natural gas, and 4.9, which is basically the same number. And then there's a tiny amount that comes in from other sources. Biomass, so that's like wood burning stove, because there are still some houses that use burning wood pellets to heat themselves. And there are some that use kerosene, for example, so that would come off the petroleum. But roughly half and half residential comes from natural gas and electricity. Almost the same thing is true with commercial, although commercial is mostly electric, but there is some natural gas that comes in there. And then the industrial sector is mostly natural gas with some other things included into it. And then the last thing is petroleum, which goes almost exclusively into transportation. There's a little bit of natural gas that goes into transportation. That's going to be like the buses that drive around with I'm natural gas. I have green leaves on the side of me to brag about the fact that you actually produce about half the carbon emissions with natural gas that you get with stuff like that, with petroleum products. Anyway, so roughly a third here, and a third here. And that's where most of the United States, this is where we get our energy from. And because where we get our energy from, that's also where we get our greenhouse gas emissions from. And most of the greenhouse gas emissions are concentrated in petroleum and natural gas. So if you really wanted to make a dent in the greenhouse gas emissions from the United States, it wouldn't so much be the electricity generation. There is some room to make improvements in the electricity generation side. For example, there's a bunch of coal goes into electricity generation. Some coal, you'll notice here, some coal goes into industrial. That's going to be for steel manufacturing, because you take the coal, you burn it at low temperature and get rid of some of the impurities, and you're left with coke, which I think is just like pure carbon. I don't know all the details about the metallurgical processes that go into making steel, but I know that you have to make coke, and you make it from coal. And so that's most of what's going on here. And then you have coal and natural gas come up here. Almost everything else in the electricity generation is some form of cleaner energy. Nothing is perfectly clean, despite statements to the contrary. But anyways, you can see here, nuclear is the largest green component of the United States electrical grid. And in France, it's basically 80% of the electric grid. There is a question. Let's see. Is natural gas cleaner? Natural gas isn't really cleaner. Natural gas is cleaner than coal. So let me talk about why. So over the course of the last 15 years, natural gas has become less expensive to produce. like to extract from the ground. And so the United States natural gas footprint has actually grown significantly, and it's displaced coal. So if you were to go back in the day, coal would have been a larger contributor to the electricity generation from a long time ago. I wonder, I might be able to go back far enough to see, no, these only go back to 2010. So that didn't help. But you could, they do have some of these flowcharts that go back into the 1980s. And when you look in the 1980s, there was no natural gas really that went to electricity because natural gas was a lot more expensive in the 1980s. And so that was made up by coal. It was basically coal and nuclear were the two sources of electricity generation and hydropower of electricity generation back in the day when they had good music and good movies. And then fast forward, as you get worse music and worse movies, the downside has been that, but the upside has been that coal has been displaced by natural gas as the fossil fuel. And coal has more carbon emissions than natural gas for the same amount of stuff. So for example, if I pull up here the drawing pad, if you look at what kind of hydrocarbons come from coal, you get stuff that looks like this. So you'll have, here's all your carbon atoms, and you have long hydrocarbon chains. And so then you have these hydrogen atoms. Wish me luck on this. It looks like a centipede, but it's not actually a centipede. So you have long hydrocarbon chains like this. Okay, which means that roughly, for the most part, for every carbon atom, you have two hydrogen atoms. So these long hydrocarbon chains, it's carbon, 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 carbon with two hydrogen atoms sticking off the sides. And when you look at this, you have, this is CH2, is this chunk of that chain. On the ends, you get an extra hydrogen atom, but in the middle of the chain, it's basically CH2, which means when you burn it, you combine it with oxygen, you're going to get one of two things. You're either going to get carbon monoxide plus H2O, or you're going to get carbon dioxide plus H2O. And this is the most common thing. You actually get better energy release if you burn all the way to carbon dioxide, because you get an extra oxygen bond in there. And so this is where the carbon emission comes from, is converting this link in the hydrocarbon chain into water and carbon dioxide. So if in the case where you have one carbon and two hydrogen atoms, you get one carbon dioxide and one water molecule. So you get a 1-to-1 ratio. However, if you get to shorter and shorter hydrocarbon chains, then for example, you'll have whatever this is. Okay, so this is 2 carbons and 6 hydrogen atoms. That's going to give you what? That's going to give you 2 CO2 plus 1, 2, 3 H2O. So you've already taken what used to be a 1-to-1 mixture of carbon dioxide and water to a 3-to-2 mixture of it. So you've gotten roughly the same amount of energy, because carbon and hydrogen bonds are roughly the same amount of energy in those bonds. And so when you break them and you form them again with oxygen, you release roughly the same amount of energy. However, you've reduced by roughly 50% the amount of carbon dioxide that you release. So instead of a 1-to-1 release of carbon dioxide, it's a 60% to 60, this is 2/5, so it's a 40% carbon dioxide compared to water vapor. And if you go all the way to methane, which most of natural gas is methane, although it does have some of these ones that look like this, ethane. Okay, so that's ethane. And then there's like butane and other forms. But the shorter the hydrocarbon chain, the better the ratio of carbon dioxide to water vapor. And if you go to methane, so methane is CH4, that looks like this, then you get CO2, 1 CO2, and 2 H2O. And this is the best you can do. So you basically cut in half the carbon emissions when you go from coal to natural gas. It's not quite a factor of 2, but it's roughly a factor of 2 improvement in carbon emissions going from coal to natural gas. And so that's why natural gas it's most definitely cleaner, right? You've reduced the emissions by half, but it's not 100% clean. It's not 100% free of carbon dioxide. So as natural gas has gotten cheaper and cheaper and cheaper, a lot of electricity production has shifted over to it. One, because it's cheaper than coal. It produces less pollutants in the end, because carbon dioxide is not the only pollutant that comes out of coal-fired power plants. You have all the ash and the tailings and stuff like that that come out of the coal-fired power plant. You release mercury. There's all sorts of filtering that goes into coal plants. Coal plants today are much, much, much cleaner than coal plants from the 70s and 80s, because there's been a lot more regulation about what kind of stuff these coal plants can put up into the atmosphere. So there's a lot more filtering that goes on to remove some of the soot that comes out of it. So that is one of the things that has actually led to the decline in carbon emissions from the United States of America, is the fact that there's been a transition from coal to natural gas as one of our major sources of electricity generation. Excuse me. All right. So if you wanted to make a big hole in the production of greenhouse gases, electricity is already working its way in that direction, especially if with expanded nuclear energy, which is what we've been talking about. So the more nuclear energy you get, the more you can replace the fossil fuel emissions with nuclear energy that has basically no emissions. Once it's built, then you have no emissions. Isn't methane, the storage of methane, more difficult than it would be than oil? Probably because methane is a gas at room temperature, as opposed to oil, which is a liquid. And so it's harder to contain a gas than it is a liquid. A liquid you can just have sitting out there, and it, it's not going to boil away, but the gas is going to boil away from these. All right, let's see. So if you want to make a big dent, the better place to focus, or another place to focus, is going to be the industrial and the transportation sector. If you completely greenify the electric grid, you're only addressing roughly a third of the energy use of the country. And you need to deal with the other 2/3 of the energy that we have in the country, or that we use in the country, which is the industrial sector and the transportation sector. And so we're going to look today at what can nuclear energy do to help displace some of these needs, or fill some of these needs without the emissions. All right, let's see. Question here. Do you not have to only look at the material balance between CO2 and H2O, but the energy balance? Yeah, so the energy that you get per kilogram, so we can pull this up. Energy density of fuels. There's a Wikipedia page that outlines the different densities of energy that you get for different fuels. And it's true that coal is not as energy dense as natural gas. I'm sorry, let me say it again. Natural gas is not as energy dense as coal, but it is still comparable. They're not vastly different. So let me come down here. What do we got? Natural gas right here. So this quantity right here, 53.6, that is megajoules per kilogram. So 53.6 megajoules per kilogram. Pretty sure that's megajoules per kilogram. Yes, megajoules per kilogram. So natural gas is 53.6 megajoules per kilogram. And if we come down to gasoline, is not as energy dense. So there's that. If you come down to, what am I looking for? Body fat, 38. So natural gas is slightly more energy dense than body fat. And if we look at coal, coal is 33. Okay, so I was wrong. It's actually, natural gas is more energy dense per kilogram than coal. One of the differences, though, that natural gas is a gas, and so a kilogram of natural gas is actually larger in volume than coal is, because coal's more compact, it's a lot more dense. And so if you do it by square meter or by cubic meter, then I believe that coal has a higher energy density per cubic meter than natural gas does, because of the fact that natural gas is a gas. Let's see, what else is there that's worth looking at? So bituminous coal, which is not as good a coal, it has a lot more ash and soot and stuff like that comes from it, because I think it has more water in it, more things that didn't completely coalify, but it's also lower. So if we look at crude oil, not crude oil, but like jet fuel, 43, diesel fuel, 45, residential heating oil, 46, but they're all roughly the same amount, right? 40 to 50 megajoules per kilogram. And if you look at hydrogen, which is one of the things we'll be talking about today, look at hydrogen. So because it's a gas, you have to have a large volume, or have to have it under pressure in order to do it. But if you do it by kilogram, hydrogen is basically, because you get two bonds with the hydrogen atoms, two bonds to oxygen, but the hydrogen atoms, but the hydrogen atoms are one proton, instead of with carbon you have 12 nucleons. And so you can imagine this being, almost an order of magnitude more energy dense, because it has an order of magnitude less mass. So there we go. Hydrogen gas is pretty dense in energy, which will be useful. If you can liquefy it, then, well, it's basically the same. But this is the per liter, so this is by volume, and you can see the difference by volume. All right, so this is why one of the things to consider when you're looking at different sources of energy, if you compare this, so chemical bonds are going to be less than 100 megajoules per kilogram, unless you're talking about hydrogen. But most of these other things are 30 to 50 megajoules per kilogram for most of the fossil fuels we use. And then you scroll up here to the nuclear fuels, and you get stuff like, okay, so antimatter, we won't worry about antimatter because it's not something that we can look at, 90 petajoules per kilogram. So if we could do antimatter, then this would be a lot more energy, certainly more energy dense, and that's not a possibility unless we had dilithium crystals and Spock could go in there and repair the antimatter or whatever chamber thing it is. But if we look at plutonium, for example, plutonium 239, plutonium or uranium, thorium, these are 80 million megajoules per kilogram. So that's 1 million times the energy density for uranium and thorium than what you get from fossil fuels. So the energy density of nuclear fuel is way, like, so far ahead of the energy density that you get from chemical bonds that they don't even really compare. It's the difference between having a $10, a $10 bill and a $10 million bill. What you can buy with $10 million is far in excess of what you can buy with $10. Everybody can blow through $10 at one sitting at a fast food restaurant. You could imagine blowing through $10 million at one sitting at a fast food restaurant, but you might get sick afterwards. And that's the difference between the energy that's available to you in a chemical bond versus a nuclear bond. Okay, so the fact that we can use these, we can create heat from a nuclear reaction means that we can use that heat for something else. And so what we want to do is look at what are the causes, or what is the energy that goes into these industrial settings, and what can we use it? What source of energy can we use? Can we replace some of the industrial applications of natural gas or petroleum with an energy that's released through nuclear reactors that doesn't go through the electric grid? So can we use the heat directly from the nuclear reactor instead of converting it into electricity and then converting it back into whatever you need at the process? So let us take a look at this. So this is our world in data, looking at greenhouse gas emissions by sector. So this is looking at different parts of the economy and where we get the greenhouse gas emissions from. So some of this is forestry, land use stuff. I'm not going to talk about that. Waste, this comes basically from when we treat our trash, and then the trash degrades and then it releases carbon dioxide. These industry things right here, this is waste, or this is carbon emissions that come from the production of these chemicals and cement. That's different than the energy that goes into making those things. So this is industrial waste carbon emissions, as opposed to carbon emissions from the energy source that allows the thing to happen in the first place. So I'll give you an example. So cement here, when you make cement, you have to reform the limestone. You have to reform the chemical bonds in the limestone from into some other thing. So there's two different chemical things that you transform it from one form into another under high temperature, but that transformation releases carbon dioxide that came from that process itself. And so that's what this industrial waste comes from. So there's actually parts of cement production that are in the energy side of this thing that are different from the industry side. So this is stuff that there's no way to control this carbon emission if you want to make cement the way that we currently make it, which involves, okay, so if you look at a cement plant, if you're going to make cement, you have limestone that you feed into a big cylinder. So here's your big cylinder like this, and the big cylinder is going to have a bunch of, it's going to rotate, so it rotates around, and you feed it in here, and then that limestone is going to work its way down this kiln, and at the other end of the kiln you have a big flamethrower. So here's a flamethrower that is blowing high energy into this area. So this flamethrower can be either, most of the time I think it's a natural gas flame, so they just have a big natural gas burner that's like a Bunsen burner, except it's gigantic, that goes up into that into this kiln. You can also pulverize coal. So you take coal, you make a powder into it, and then you blow it up into here and then light it on fire, kind of like a grain silo fire. So you pulverize the coal, send it in, and you light it on fire, and then you treat it the powder is small enough that it convects with the air, and so it acts like a regular flame. So yeah, that is the thing. So CaCO3, that's calcium carbonate, turns into CaO and CO2. And so that release of CO2, so let me write this down. So you've got calcium, CO3, it turns into CaO and CO2. Okay, so this thing right here, that is what you need. This forms clinker. Clinker. And that's what you need to make cement from. So this is what you're trying to get. And this CO2 gets released. And that's the CO2 that goes into this, that goes into this waste right here. Okay, there is some stuff up here that is not included here, but the energy that goes into the flame, the energy that goes into this flame, is not included in that gray wedge of that pie chart. Okay, so you send the stuff in, you have this big flame, you have to heat it up to high temperature in order to break apart these bonds and form what it is that you're looking for. Okay, so this is cement production. Steel production, you have a similar release of stuff, because when you have steel, there's always some carbon left over. When you have iron ore, there's always some carbon embedded in it. And typically the way you want, because you want to control exactly how much carbon is in there, you start with steel, you melt it down, and you want to get rid of the carbon. And so the way you get rid of the carbon is you have a big blower. So here's your big blower, and you blow oxygen into it. And the oxygen comes through the steel and binds with the carbon that's inside there and releases carbon dioxide. So this is called a something oxygen furnace, a big old oxygen furnace, something like that. So that is these are some examples of the kinds of sources of carbon emissions that don't come directly from the burning of the fossil fuel, but are a byproduct of the chemistry that you're doing. There is a question here about geothermal energy. So geothermal energy is, it's a small fraction of what we get in the United States. There are some efforts to increase the geothermal production in the United States. It can work fairly well. So this is a brief aside, and we'll get back to what I was talking about. If you look at a map, you can imagine doing pretty well with geothermal in the state of Nevada. So if I scroll this out, where's my... It's not letting me... There we go. There's the layers. If I scroll this out to the satellite image, or better yet, I'll just do the terrain map. So if I go to the terrain map and I scroll out, the Great Basin area is where the crust has been stretching apart. So we can see the Rocky Mountains right here. Well, okay, so this is like the depth of the Rocky Mountains, and then there's this Colorado Plateau that's running in between them, and then this is the front, the Wasatch Front, that is kind of the edge of the Rockies. So the Rockies is this kind of big square area. You hit Denver, and then you turn into Kansas. So half of Colorado is actually Kansas. The other half of Colorado is actually Utah. And the mountains in Colorado and the mountains in Utah are all part of this big kind of same formation. And it was the Rockies kind of run down like this. So the Wasatch Front is the western edge of the Rocky Mountains. And then from here over to the Sierras, you can see these mountain ranges that run roughly north and south. They kind of spread out like they're fanning apart. And they fan apart because this part of the continental crust is rotating up towards the north. So it's stretching out right here, and it's compressing up here. So if you look at Washington, you have these ridges. This was supposed to be the terrain map. Why did it go back? Come on, terrain. There we go. So you have these ridges in Nevada, right here, and that's from the crust spreading apart. So the crust is spreading apart like that, and the ridges remain, and the valleys sink down in between them. So you get the basin and range formation. You have a range, and then a basin, then a range, then a basin, then a range, then a basin, and that's from the crust spreading out. And that's because the western United States is rotating and slamming into Canada, and Canada isn't moving, and so you have these bumps up here. These are the crumple zone. That's where the land is coming together and popping up and forming these ranges that run east to west in eastern Washington. Okay, and so geothermal energy in Nevada is promising, more promising than other places, because the crust is spreading out like this, it's getting thinner. And so the crust in Nevada is a lot thinner than it is in California or Utah. Well, I mean, this part of Utah is kind of thin as well. So this is a good place for geothermal. There's a lot of hot springs and stuff like that that run through all of this area. So there's a bunch of hot springs down here. There's hot springs all throughout southern Idaho. And that's from the fact that the crust is kind of thin. It also helps that there's a big hot spot underneath Yellowstone National Park. And so, but other parts of the continent, for example, in Colorado, it doesn't really make sense to look for a lot of geothermal because the crust is thicker here. All right, so anyways, that's the answer to that question. Geothermal, there are some places where it makes sense, and there are other places where it doesn't make sense. Okay, now back to this. So we have these different uses of energy in industry. Iron and steel production, you have to melt it down, you have to put carbon back into it, you have to get rid of the carbon that's already in the ore and make the proper measurement or like proper adjustments to the amount of carbon that's in the ore so that you get the right kind of steel that you want to produce. You can see petrochemical, so that's like oil refining, chemical and petrochemical. Oil refining, the production of, for example, ammonia. So if you want to make fertilizer to grow food, because we all like to eat, most of us like to eat, you need to have ammonia. And the way that you make ammonia is by the following process. So you want to make ammonia, in other words, you want to make fertilizer that you can use to grow plants with. What do? Well, you start with N2, so that's whatever this is called, nitrogen, and you want to make NH3, right? This is ammonia, NH3. And so you need a source of hydrogen. That source of hydrogen is usually water. So you start N2 plus H2O. There's going to be some stoichiometric coefficients out here to get the equation to balance out correctly. But roughly speaking, you're mixing nitrogen and oxygen together to get NH3. But you have to do something with the oxygen here. And what you do, well, for one thing, the only way to get this process to take place where you get NH3 is you have to add some energy to the system. You have to, because oxygen bonds are pretty intense, and so you need to add energy to the system to break these bonds apart and allow them to reform. So this is called steam reforming. And steam reforming is a common, when we talk about oil refining, we'll get into that as well. So you want to reform these bonds to be able to produce something like this, and you do that at high temperature. So in order to get the high temperature, you bring in CH4. So you bring in natural gas, and you light the natural gas on fire, and then the carbon will bind with the oxygen, and so you get NH3 plus CO2. So you get carbon dioxide release in this steam reforming process. So you're mixing this in with all these things, and then you raise the temperature up, and the bonds all rearrange themselves to get ammonia and carbon dioxide. And so that is, thank you for that sub, I appreciate that. So that is how you make fertilizer that you need to, well, for all sorts of things. You use ammonia for a lot of stuff. It's not just fertilizer, but that's the main application of it. But you use it for like cleaning supplies and things like that. And so that's where you're going to get carbon emission because you're using CH4 as the fuel to heat it up with, and also as a way, a source of carbon to rearrange these bonds, like a place for the oxygen to bind afterwards. So these are, that's where this carbon emission comes from chemical production. For petrochemicals, when you're refining oil, and so I actually have a picture of an oil refinery here. When you're refining oil, you bring crude oil in. So crude oil comes in here, you warm it up, and then you put it in this distillation tower. And crude oil is a mixture of all sorts of chains of different lengths of hydrocarbons. So you have some hydrocarbons that look like this, like the one that I showed you earlier that look like a millipede. So here's this huge hydrocarbon chain like that, and you get some methane in it. So you're going to have all sorts of different lengths of hydrocarbon chains. You're going to have really long ones, you're going to have some intermediate ones, you're going to have some short ones. But they're all mixed together in this crude oil. And so how do you separate them? Well, you have to separate them through some kind of physics because, well, that's the easiest way to do it. Each of these different substances has a different boiling point, or when it's gasified, when you turn it into a vapor, this one is lighter and so will tend to rest higher. If you vaporize all of these things, the more dense material, which is going to be these long chains, is going to rest at the bottom, and the less dense material is going to float on top of it. And so that's what you do in a natural gas refinery, or I'm sorry, in an oil refinery. You bring in crude oil, and then the longer the hydrocarbon chains, the lower they are going to rest in the gaseous form. So you have to vaporize them all here, and then it gets in this distillation tower, and different lengths of hydrocarbon chain will rest at different levels in this distillation tower. And then you siphon off the material that condenses at these different heights. So, and then up at the very top, you get basically methane coming off the top. So this is C1 to C4 gases, so this would be methane up to whatever that is. But you can see different lengths of hydrocarbon chains will settle at different heights in this tower, and then you use it for different reasons. So you can use it for like what's the stuff that you clean it with? Like like if you want to clean off oil that's on your hands. I used to use it all the time when I made model airplanes. Anyway, so there's cleaning supplies that are going to be here. You're going to have propane up here, natural gas, acetone, that's the one. So like acetone, those kinds of things are going to have different hydrocarbon chains in there. Petroleum that goes into cars, kerosene, so that's for home heating and jet fuel, diesel engines, like diesel oils and stuff like that. And then down here, you're going to have oils and waxes and different things with different lengths. And you can see like C50, right? That's 50 carbons with hydrogen bonds. And you compare that to methane, which is CH4, like 1 carbon and 4 hydrogen bonds. And then you have other fuels down here, like the really heavy stuff for different kinds of processes. And then the residue that's left over, the stuff that's got really lots of carbon in it, you pave the road with it. So these are materials that you use for tar, roofing materials and things like that. So that all comes from crude oil. It separates out into these different things, and then you use the different hydrocarbon lengths depending on what you need. Now, if you want to, so here's a question. The levels at which the chains are each respective fuel, is it explicit as the drawing suggests? Pretty much. I think this is pretty much what it is. You might do further separation. For example, if you have an oil that you're going to use to lubricate nail clippers, it might be different than the oil that you use to lubricate a car engine. And so they might do further separation at this point. That I don't know. We pave the road with oil because, one, you have this stuff left over, and two, it makes an impermeable, it makes it so it's waterproof. One of the things I was going to point out here is that, so if you don't like this mixture, if the crude oil that you have is not producing the mixture that you want, you can do things to reform these. So for some reason you needed heavier hydrocarbon chains, longer hydrocarbon chains, you can do some high temperature chemistry to rearrange the bonds to remove some of the hydrogen from, okay, so let me draw this picture. Suppose that you have 2 methanes, so they both have, so these are 2 methane molecules, and you want to make a longer hydrocarbon chain. What you need to do is remove 2 of the hydrogen atoms. You need to get rid of this. And once those 2 hydrogen atoms are removed, then you're going to get the carbon-carbon bond, and now you've doubled the length of that hydrocarbon chain. So you're going to get something that looks like that. Okay, not this thing. That's not in there. And so you need to remove that hydrogen, and so you could do it by like adding oxygen to the system and then extracting the water vapor from it. So you can make the hydrocarbon chains longer by removing hydrogen from that substance, or you can shorten the hydrocarbon chains if you add hydrogen to the substance. So let's suppose that you have a really long millipede hydrocarbon chain, so it's got like 50 carbon atoms on it. So you have something that looks like this. If you remove, or I'm sorry, if you add hydrogen to this mix, so here's 2 hydrogen atoms that would like to join this chain, the only way that they can join is if they break one of these carbon-carbon bonds, and then one of them joins over here and one of them joins over there. And so you can take long hydrocarbon chains and crack them. I think it's called cracking. You crack them, and then by adding this hydrogen to it, but you have to have enough energy in there to break the initial carbon-carbon bond to begin with. So you have to have, they have to be moving around fast enough so that when these molecules bump into each other, you break the carbon-carbon bonds. And then if there's some hydrogen in the vicinity that you can add to the mix, then those hydrogen atoms can bond in there and break something, into different lengths. So that's a way of taking what you have from the crude oil and converting it into something else that might be more useful, to get a slightly different mix of byproducts that you have from the distillation process or from the refining process. Now, one of the things that can happen here is if you look at the temperatures that you need to do the oil refining. So crude oil comes in, you do the refining. It's 600 Celsius is the lowest, is the highest temperature that you see here. That's the temperature where these things vaporize, is 600 Celsius. Everything above here vaporizes at lower temperatures. So you can see 20 degrees Celsius is when you evaporate some of the propane and things like that. And so if you can heat this crude oil up to 600 degrees, then you can do this refining process. Right now, what they do is, I believe, for the most part, they take some of this byproducts that they're making and feed it back in here. So they actually supply the heat source from the actual crude oil. So they take the crude oil, they pull it out, and then they burn some of that crude oil to drive the burners that raise the temperature up to boil things. And so that's going to be releasing some of the greenhouse gases. If you could replace this with some other energy source at 600 degrees, then you've eliminated something. I think it's like 15%. We'll see some numbers in a little bit. I think it's like 15% of the energy, or 50% of the carbon emissions from petroleum comes from the refining process itself. So you have an oil company, they're burning 15% of their profits in the refining process itself, simply to be able to partition it out into the different products. So if you could replace this and somehow raise the temperature without burning a fossil fuel, then immediately the oil companies become 15% richer because they can sell, they don't have to burn their profits in order to make this stuff. And so there's a good reason to look for alternative sources, aside from the fact that, then you save 15% of the overall emissions by eliminating, the demand for oil isn't really going to change all that much. It's going to continue to grow, at least for the time being. But you eliminate 15% of the emissions just in the processing part. So this is where some of these Generation 4 nuclear reactors can come in. So there is a question here. If we found any good carbon capture mechanisms, not that I know of. I mean, there are a variety of carbon capture mechanisms, but it usually requires that you have a really high density of carbon dioxide to make it efficient. So you could do it, the best places to do it would be at an industrial plant where you're burning a lot of hydrocarbons to do the carbon capture. It wouldn't really work on a car because it's too diffuse. There's another comment. Is it basically what happened when they hit the Kuwait oil fields on fire? Yes, there just wasn't enough container to capture all the burning stuff. So if we look at nuclear process heat, this is if you take heat directly from the nuclear reactor. So this is not taking heat from the nuclear reactor and boiling water with it and producing steam to drive a turbine. Instead, this is saying you have a nuclear reactor with high temperature material in there, and we're going to siphon off that high temperature material and use it as the heat source. Okay, and so the Generation 4 nuclear reactors that we discussed last time operate at these high temperatures. That's one of the things that marks the Generation 4 nuclear reactors from the other ones, is the fact that they operate at high temperatures. And so here on this graph, so this is worldnuclear.org. This shows some of the different chemical processes. Hopefully this is big enough. Can I open this image? Open in a new tab. Maybe I get a bigger version. Yeah, here we go. Okay, so this is showing some of the different processes that are going into, that currently take fossil fuels and therefore produce greenhouse gas emissions, and the temperatures where this takes place. So you can see that glass and cement manufacturing is at the top. Cement manufacturing has to take place at like 1500 Celsius, I think is the typical temperature in those kilns where they're producing the clinker, is more than 1200 degrees. Glass I don't know much about, but cement is the largest emitter in that section. So direct steel making manufacturer, you can see that the range of temperatures that they need is between 600 and 900 Celsius. Thermochemical hydrogen production. So hydrogen production will be important. We'll talk about that in a minute. Steam electrolysis, so this is producing hydrogen gas from steam directly. Methane reforming. So methane reforming, this is fertilizer production. Well, in part, like some of methane reforming is fertilizer production. There are other reasons why you might want to reform methane. So this is fertilizer production. That, again, has to take place at high enough temperatures to rearrange the chemical bonds. And the temperature looks like around 600 Celsius. Petrochemical, so this is producing a bunch of different things. Petroleum refining. Petroleum refining is actually quite a bit cooler, right? You can see 600 was the peak on that last graph. You can see that most of the chemical refining, or the oil refining, can take place between 300 and 400 Celsius. Shale and tar sand oil production. So right now when you do, when you're extracting oil from tar sands or from shale, you have to put in high temperature water, high pressure, high temperature steam, basically, to drive the oil out of the pores of the rock. And so that takes some relatively high temperatures to do that. Pulp and paper production. So when you make paper, you grind up all of the wood pulp. Like you make the wood pulp, it's like a slurry. And then you have to evaporate all of the water out of that system to eventually form the paper. And so that takes quite a bit of energy. Right now, the pulp and paper production, they use a lot of biofuels. Basically, you make it out of the trees, and then you have the sawdust that comes from those trees, and you use that, you burn that stuff in order to heat up the water, to boil the water off to make the paper. So you could replace that use of, it's a biofuel, so it's got a slightly different environmental impact than fossil fuels do, but still, right? There's carbon emissions that come from it. So, anyways, pulp and paper production is also fairly low temperature, and then you have down here at the bottom is desalination. So, removing salt from seawater. There's actually quite a bit of desalination that needs to take place, especially around desert areas. Saudi Arabia, for example, has water desalination everywhere around the Mediterranean, the north coast of Africa. Water desalination, if you're a populous city by the ocean, like Singapore, they also have water desalination where they bring in ocean water, and they have to have some form of energy in order to run through the process of extracting the salt from the seawater. So but you'll notice here that that's fairly low temperature. It's right around the boiling point. Okay, now this is the types of nuclear plants are here on the bottom. Let me zoom in a little bit more. And you can see the temperatures that are supplied or that go on in the reactor itself. So with light water reactors and heavy water reactors, the temperatures where those operate is around 200 Celsius, 300 Celsius, something like that. And so you can use light water and heavy water reactors, which is the current generation of nuclear reactors, to do, maybe do pulp and paper production, to do district heating. So they'll heat up water and then they'll pipe it out to different areas. There's quite a bit of district heating from nuclear reactors in the old Soviet bloc and in the northern part of Central and Eastern Europe. So they just have a nuclear reactor, they make hot fluid, and then they pipe it around the area so that people can just use that directly instead of using natural gas to heat up water in their homes. And you can use it in place of a furnace as well. So you run warm fluid through something, you heat up the floor with it instead of burning natural gas like we do pretty much everywhere else. So if you have a light water or heavy water reactor, you can replace some of the applications of fossil fuels by just transferring that heat directly to those things. Or you can use it to desalinate water, which otherwise would take electricity or something like that to do. There's probably a variety of ways to desalinate water. I'm not really an expert in water desalination. I'm sure that it tastes just fine when you're done. Okay, but then developing reactors, these are the ones that we were talking about with our last stream. So the small modular reactors, again, these are light water reactors, so they're basically operating at the same temperatures. We have a liquid metal reactor. So the reason you want a liquid metal is because it doesn't boil, and so you can have your coolant can be at a higher temperature. Instead of having to worry about the boiling point of water, you might have a sodium cooled reactor where it's not going to turn into a gas until you get way up there in temperature scale, like thousands of degrees. And so if you have a liquid metal reactor, and these are ones that are developing, like that are currently right near commercial applicability. The high temperature gas reactor, I know that they're working on that at Idaho National Lab. But you can see these liquid metal reactors and the high temperature gas reactors, then you can start using the temperature of the coolant in the reactor core, because the reactor is going to be at 1,000 degrees. You can start using that directly in these industrial processes and replacing, pulp and paper production. You can use the liquid metal reactor, petroleum refining. So if you have a molten salt reactor, so down here at the bottom, so these are future reactors that aren't yet ready for prime time, or have some development still to go. A molten salt reactor, so if you have thorium, a thorium reactor, you can do oil refining directly from the reactor. You can also do methane reforming. For some processes, you can do methane reforming with a molten salt reactor. So instead of burning natural gas to make fertilizer, you can use the heat directly from the nuclear reactor to supply the energy that you need to do that production directly. Another thing that you can do, especially with like high temperature gas reactors, is, do they have it up here? Yeah, right here. Thermochemical H2 production. So hydrogen production right now is done by probably burning natural gas in order to supply the high energy that you need to rearrange the bonds in order to perform, or in order to form hydrogen gas. And hydrogen gas is used in all sorts of different industrial applications. For example, with cracking for long hydrocarbon chains, if you want to break it apart, you have to have a source of hydrogen that you put in there. And so thermochemical H2 production, so thermochemical means that you're burning something, H2 production. And if you have a high temperature gas reactor, you can do all of this hydrogen production directly from heat from your reactor without having to burn a fossil fuel to do it. And you can almost do some of this. You can do even with the molten salt reactors and the gas cooled reactors, despite the fact that they're more around. They peak at around 800 Celsius, where the high temperature gas reactor peaks at around 1,000 Celsius. Right? Here's 900. So, anyways, this is some of the. Once you have a source of energy at a high enough temperature, then you can start replacing this sector. You can start replacing the fuels or the energy sources that go into this sector. You no longer need to use petroleum to refine the oil. You no longer need to use natural gas to make your cement or to make your fertilizer. You don't have to use natural gas to make your fertilizer anymore. You can use air and, say, hydrogen gas that you produce directly, or air and water directly with the temperature or with the heat that you provide from the reactor, because it's happening at a high enough temperature. So high temperature chemistry is a major source of fossil fuel emissions today. And most of that, as we see from that plot, or from this graph, most of those high temperature chemical processes that we rely on as a global society can be replaced. The sources of energy can be replaced with nuclear reactors that are operating at high enough temperatures. Light water reactors don't operate at high enough temperatures to replace much of it. They can do some, but not all. But when you get to some of the Generation 4 nuclear reactors that are operating at higher temperatures, then you can start really digging into the fossil fuel emissions or the carbon emissions that come from the industrial sector. Let's see. As long as we don't have nuclear reactor meltdown at high temperature, we should be fine. And the advantage of the Generation 4 nuclear reactors, which all of these things are, liquid metal reactors, high temperature gas reactors, the molten salt reactors, these are all Generation 4 reactors. There's no meltdown. I mean, like, the chances of a meltdown are tiny. For one thing, what is a meltdown? In a light water reactor, a meltdown is when the fuel escapes the fuel rod and becomes a liquid. But when you have a molten salt reactor, the fuel's already a liquid. So it's already melted down. There's no mechanism for it to escape. And if it does escape, it will escape through the drain plug at the bottom, and then it automatically turns itself off. Let's see. The danger is in significant radiological release. Contained meltdown is not an actual health risk. All right, now let's take a look at some of the other things that it mentions in this article. So this, again, this is worldnuclear.org, and they go through some of the applications of things. Process heat applications. So for electricity production, one of the things that we talk about with electricity production is what cycle do you use to generate your electricity? What do you use to spin your turbine? So most reactors, currently most reactors use the Rankine or the steam cycle, right? Because that's up to 700 degrees. So anything lower than 700 degrees, you're going to be using the steam cycle, which is fine. Natural gas generators don't use the steam cycle. But coal-fired power plants use the steam cycle and stuff like that. So if you have a coal-fired power plant, you're going to use the Rankine cycle, which is the steam cycle. The natural gas power plants are different. They use the Brayton cycle. So the Brayton cycle is like the jet engine cycle. The jet engine, you bring in air, you compress it, you light it on fire, and then the exhaust comes out the other side. So you still have the same steps of bringing in air, compressing it, raising the temperature, and then exhausting the material. But how do you go through that? And the Brayton cycle is basically a jet engine. So the natural gas power plant is a jet engine set on a block, and then you run natural gas through it instead of jet fuel to create to spin the turbine. So one of the advantages that you get with a natural gas power plant is that you can use the exhaust from the Brayton cycle. Even though the Brayton cycle itself operates at really high temperatures, the exhaust is also going to come out at high temperature. And so you might go from 900 Celsius and then drop it down to 500 Celsius. But 500 Celsius is still high enough temperature to run the steam cycle. And so when you look at a natural gas power plant, you'll get what's called a combined cycle natural gas power plant. Combined cycle means that you have a Brayton cycle, the natural gas plant runs like a jet engine, and then you take the exhaust from the jet engine and feed it into a steam cycle, and then have a second cycle where you get electricity from the exhaust from the first cycle. Some natural gas power plants are combined cycle and do both. However, if you're backing up renewable energy, you can't use that cycle because it takes a long time to get the cycles working together, where the boiler for the steam cycle is operating efficiently. And it doesn't ramp up fast enough for when the sun sets. So the sun sets over the course of an hour, hour and a half. And so it takes longer than that to ramp up a typical combined cycle power plant. And so the peaker plants that correct for or that deal with intermittency in renewables are the direct Brayton cycle with no combined cycle component. There are always companies that are working on improving these things, so that might change in the future. But for the moment, this is what's going on. Oh yeah, zoom in a bit. I can try zooming in and see what I can get from it. Let's try this. Okay, so that's what I was looking at. Okay, so utility applications aside from, so what can you do with nuclear process heat? So if you have nuclear process heat at 900 degrees, then you can heat up a gas and do electricity production through that same thing that you would get from, instead of burning a fossil fuel to raise the temperature of the gas, you could inject high temperature gas into your turbine and then produce it that way. Utility applications, so this is desalination. That's going to be increasingly important as people continue to move into the deserts. Another thing you can do when you get up to 900 Celsius, so when you cross this threshold where there's probably certain kind of chemical bonds that where you transition in those chemical bonds at high temperature, you can make H2, so you can make hydrogen gas from steam reforming directly from methane or high temperature electrolysis. And if you can go above 950, so this is not easy to do. The only thing that can go above 950 right now is the high temperature gas reactor. Then you can get H2 production directly. So you basically just put water in and it splits it apart and you get hydrogen and oxygen out of that mix. Now, what can you do with hydrogen? There's all sorts of things you could imagine doing with hydrogen gas directly. Now, there is a danger, like hydrogen's a little bit harder to deal with than natural gas because it tends to leak into the metals that you contain it in and things like that. But some of that you can imagine engineering your way around, or you just use it more quickly, like you don't store it as long as you would natural gas. But some things can get brittle in the presence of hydrogen gas. So you have to come up with a way to work around it. You have to come into the supply chain process to limit the amount of time that the critical materials become weakened by the presence of hydrogen. So it's not like you can immediately turn this stuff on, but you can imagine turning it on. And it probably won't take all that long, I don't think, to, if you can make a lot of hydrogen gas for cheap, then it probably won't take all that long to come up with whatever cycle, like whatever processes you need to be able to include it into your energy mix. Now, why would you want direct H2 production? Well, for example, you can make long hydrocarbon chains into short hydrocarbon chains. Another thing you can do with it, at least you could imagine the following thing happening, is suppose that you want to make cement. So here's your kiln to make cement with, and you have the clinker you have the limestone coming in. You're going to make clinker as you come down here. It's rolling around on this roller. And if you have a tank of hydrogen, then instead of having a natural gas flamethrower that's blowing up into this kiln, you have a hydrogen gas flamethrower. And so you use a hydrogen flame inside this cement manufacturing place. And then you use that as your energy source instead of natural gas. And so you'll still get the carbon emission from the chemical process that you're going through, the conversion of calcium carbonate into clinker and CO2, but you don't get the combustion of carbon in the flame itself. So you're not using coal, you're not using natural gas, you're just using hydrogen gas. So this is one place where you could imagine replacing a fairly significant portion of our global carbon emissions by using the hydrogen gas as the energy source. Like another example would be, almost every house has a burner of some sort for natural gas, like our stoves, our hot water heaters, our furnaces use natural gas. One could imagine replacing some fraction of that, if not completely, replacing it with hydrogen gas. So you burn hydrogen gas on your stove instead of burning natural gas on your stove. So you remove the carbon and you just burn hydrogen directly, in which case the exhaust that comes off of it is water vapor. Now, it's not necessarily a trivial thing to do, but it's something that could be done. I wanted to look at this right here. Okay, so we can see like this chemical and petrochemical stuff, this 3.6%. So you could imagine converting almost all of this 3.6% of global carbon emissions, eliminating completely with nuclear process heat. That's roughly the carbon emissions of Japan. That's like the third largest economy in the world. Is that the third largest economy in the world? Japan's up there. So it's certainly in the top 5. You could replace the entire carbon emissions from Japan by switching from fossil fuel sources of energy to nuclear process heat. A lot of the stuff over here, paper and pulp, machinery, all these things, some iron and steel production could be switched over to nuclear process heat. And energy in industry right now is 24%. So you could imagine, maybe you only get half of that. You eliminate 10% of emissions globally by switching the easy stuff over to nuclear process heat. Energy use in buildings. So this energy use in buildings, that's including like heating up the buildings. Commercial, it's basically split almost 50-50 between residential and commercial. And that's another 20%. So if you could imagine cutting this in half and having, certainly in smaller environments, I mean, I guess it depends. Like you'd have to figure out like where is it most efficient to apply this stuff. But you'd have nuclear, you take the heat from the nuclear reactor and pipe it into different areas. So residential heating, which is what we've already seen in some parts of the world. It's already being done in some parts of the world. You can imagine expanding that so that instead of burning natural gas, you're just piping in some kind of warm oil, like a heating. It's not an oil that you burn, but rather it's the fluid that you use to carry heat. And so you heat up your floors instead of burning a natural gas burner and then blowing it into the room. You heat up the floors in the room by piping this warm fluid through your home. And so that could be something that is replaced by nuclear process heat. So you replace natural gas with that. So these are, it requires some infrastructure. So there's a bunch of things that would go into it that would have their own carbon footprints associated with them. But you can imagine as you replace the infrastructure, you include this into the mix. And now you're talking about 20%. If you get rid of electricity use, so if you start making, it doesn't look like electricity is in here, but if you make all of your electricity from nuclear instead of natural gas or from coal, then you can imagine getting the bulk of this. And so that's a huge reduction in the carbon footprint that you would get from those things. And then when you're talking about road transportation, this is all liquid fuels for the moment. But if we want to electrify, for example, electrify most of the cars, then where are you going to get your electricity from? Are you going to get your electricity from fossil fuels, or can you get it from some other place? A couple of comments here. Nuclear power plants take years to improve due to the amount of regulations they have to go through. That is correct. And in fact, so I had an interview with Richard Muller, who is an emeritus professor at Berkeley. And one of the things we talked about there is he mentioned that it costs half as much money to build, if you have the same nuclear plant and you want to build it in South Korea and you want to build it in wherever, Oklahoma, it costs twice as much money to build it in the United States as it does in South Korea. And it's mostly from regulation. So let's see. So the U.S. is not a fan of making nuclear power plants in our soil. Well, it depends on who you're talking about. Okay, let's take a look at, are there other processes that it's talking about here? Oil from tar sands, like this is all part of the mix of things that we discussed already. We'd already talked about oil refining, coal to liquids. So this is a way of taking coal, like the long hydrocarbon chains from coal, you melt the coal down into a liquid form, and then you can separate, you can crack the large hydrocarbon chains and form smaller ones, so you can liquefy that and then turn it into kind of highly processed fuels that you can use in cars. So the Fischer-Tropsch process developed in Germany in the 1920s because Germany has a lot of coal. As they're exploiting now that they're turning off their nuclear plants, they're like, we got all this coal we can use. Good for us. But because they were cut off from a lot of sources of oil during World War II, they used this to turn their coal into liquid fuels. And so this is something that you can do also with nuclear process heat because it happens at relatively low temperatures, certainly lower temperatures than 1,000 degrees Celsius. What else do they have on this? District heating, we've already mentioned that this is being used. This mentions a couple places where they're already using nuclear plants. A lot of it's in China to do heating of some municipality. Anyways, so these are some of the applications that we can have with the heat that comes from nuclear reactors. And the higher the temperature of the reactor, the more options there are available for the use of the heat that comes out of it, as opposed to only using nuclear energy to supply the electricity. So anyways, lots of options. And it seems like yet another motivation for producing some of these next generation reactors that are going to operate at higher temperatures. When you make the electricity, you get higher efficiency from the electricity generation. And when you're not making electricity, you can siphon off that energy, or if you don't make electricity at all, you can siphon off that energy to do other things that are needed, like making clean water, or making hydrogen gas to use in other applications, or making fertilizer, or whatever the case may be. Okay, let's see. Any other questions or comments? Let's see. Why aren't we building huge batteries of some sort in the ocean? Well, one of the things when you're talking about batteries don't really have a very high energy density. So we saw earlier, I don't know if it's still up, energy density. Okay, energy density is here. We saw earlier when you're looking at hydrocarbons, you're talking about 50 megajoules per kilogram. If you look at battery power, that's way down here. So lithium ion batteries is way down here at the bottom. So even this one, I've never seen it. Battery, lithium air rechargeable battery, 9 kilograms. So that's 20% the energy density. I think typical batteries, like these are more normal batteries, the kinds that you put in your remote control and stuff like that. Let's see. Alkaline battery, 0.48. So that is 1% the energy density. So if you have a battery, if you have a vial of gasoline and a vial and one AA battery that are the same size, you'll get 100 times the energy out of the gasoline than you get out of the battery itself. So batteries aren't particularly highly energy dense, and so if you try to, you do have to have really large batteries if you want to do that. If you're trying to use, salt water for your battery, then it's not as, the energy density is pretty low, which means that the environmental impact, aside from carbon emissions, because there are environmental impacts that are different than the carbon emissions, it can have a fairly large footprint. Same thing with flywheels. I think they have a flywheel on here. So the flywheels, again, the energy density is pretty low. So if you want to power a city, it's not going to be with flywheels. If you want to regulate the voltage in the line for small changes, like if you have a half a volt change that you need to regulate in the line, then a flywheel makes sense. But storing full grid capacity stuff with a flywheel it's not really viable. Okay, let's see. Like water at a 100-meter dam, 0.0009881. So if we look at the sources of energy that people are imagining, one of the advantages you have with the battery is that you can charge it multiple times. So it's not just a single use. So you can make up that difference by multiple charges, but that doesn't mean that it has the energy output. It doesn't have the wattage, the power capacity that you have from the fossil fuels. You can burn fossil fuels fairly quickly and release the energy all at once, which is what you need if you want to power on a light bulb. It's going to take a certain amount of energy per second coming through. And so it's not just the total energy, but it's how quickly can you deliver that energy that's important. So gravity is, when you're talking about the gravitational coupling between things, we've already seen the nuclear coupling is a lot stronger, and then the chemical coupling, the electromagnetic coupling is weaker than that, and the gravitational coupling is the weakest of them all. And so if you have 1 kilogram of water and you're raising it up into the air, you're working with the gravitational field, which is the weakest of the fields. Gravitational field is much, much weaker than the electromagnetic field, which is much, much weaker than the nuclear field. So there's that. So it's the advantage that you have with gravity and water storage. It's very weak per kilogram, but a reservoir has a lot of kilograms in it. But they're still not, they have a big footprint. Anytime you have an energy density that's really low, you're replacing, I guess, the perceived danger from the substance with a large footprint environmentally. So if we were to look, for example, at in the Las Vegas area, and I don't know why I always have to keep saying this, but I will. I'm not opposed to nuclear energy. I'm not opposed to solar energy, but I am opposed to people not understanding what the implications of solar energy are, like just blindly adopting solar energy for without being fully informed about it. So here's a solar power plant in the Las Vegas area. Okay, so you see all these solar panels here. Here's this dry lake bed, solar panels over here, solar panels over here. All of these solar panels combined are, the way that they report it is that it's 800 megawatts, I believe, is the amount for this whole area. 800 megawatts, and they say, this is 800 megawatts. But that's a little bit deceiving. It's a good way to sell it to somebody, but it depends on how informed the person you're selling it to is. So it's 800 megawatts peak capacity. That's like high noon on June 21st. That's how much energy you can get out of this. Peak capacity is 800 megawatts. The average capacity that you have for a solar power plant is going to be something like 20% of that. And so it's not 800 megawatts, it's like 100 megawatts. And so and it doesn't happen all at once, right? It fluctuates over time. And so you have to be able to make sure that you can accommodate that in the grid. Now, fine, so we have a source of energy, but it's only 100 megawatts, and it has a fairly large footprint. If you compare that to a natural gas power plant, so if you come up into Henderson, right here at this corner is a natural gas power plant. So here is a natural gas power plant. You can see all the different generators that are connected to it, or that are part of this plant. This thing is some number, like how many gigawatts is this power plant? It's Edward Clark Generating Station. Let's take a look at that. Edward Clark Generating Station. Okay, it's 1 gigawatt. So this thing is 1 gigawatt. That's 10 times the energy, the power production as that whole solar plant on the average output of that solar plant. 10 times the energy production. And here's how big it is. You know, it's what, like not even half a kilometer. So it's a couple hundred yards across. Okay. So it's like what, the width of the bottom of this arrow. So now it's the width of the bottom of the arrow. And I scroll down here, right? You could put 10 of these things, you could probably put almost 100 of them in the same footprint that you have with the solar power plants. You know, these have carbon emissions, and the solar power plants have far less carbon emission associated with them. But the amount of real estate that it takes to produce a power plant, you know, this is 1/10 of that one power plant. It takes, you know, so there you go. It's not without its environmental impact, even though, so there's more to environmental impact than just carbon emissions. If you were to look at the emission, or like the amount of energy that you get from a nuclear power plant. So if we come over here into Arizona, the Palo Verde nuclear plant is the largest nuclear power plant, I think, in the United States. It's certainly the closest to us. It's around here. I can never find it when I'm looking for it, but it's in this area. Let me look for it real quick. Palo Verde. Right there. So this is roughly the same size as that. Here's the power station. It's got 3 reactors. It's roughly the same size as that natural gas generating plant. And yet this is like almost 4 gigawatts. So there's the difference. The amount of energy that you can produce with the high concentration of, the amount of electricity you can produce from high concentration of energy, especially from like nuclear energy, that's the advantage that you get with high energy density materials, including fossil fuels. So in the end, that's the trade-off that people need to be aware of. And I think people are increasingly becoming aware of the landscape, like the real estate footprint of renewable energy. They're like, wow, this actually is really big, and we're not quite getting everything that we expected out of it. So it looks like there's a bunch of solar generating power plants here as well. Right, Sunstreams 2, that looks like a solar power plant right there. So, you know, it makes sense in certain areas. It might not make sense in other areas. It's just something to be aware of. It's not quite the unicorn poop that people sometimes think it is. Yes, and one of the things that we're going to do in the future is we're going to do some of the calculations about, like, what does the waste stream look like? So we know what the waste stream looks like for fossil fuels. We know what the waste stream looks like for nuclear power plants. The waste stream for nuclear power plants, because you get 1,000,000 times the energy, the waste stream is significantly smaller than what you get from other sources of energy. And we don't yet know what the waste stream looks like for these kinds of power stations. These are just being built. They're just being turned online. If you wait 20 years, and now you're at a position, 20 or 30 years, and now you're at a position where you have to replace all of these solar panels, that's when the waste stream is going to hit us. So we're putting a lot of stuff in the pipeline, and I don't think that many people really appreciate what the waste stream is going to look like for these different sources of energy. You know, maybe we can eat it when it's done, or I'm sure some of it can be recycled, but not necessarily all of it. But what is the waste stream going to look like, especially when you consider the fact that this is only going to produce 100 megawatts. The unit of power plants is a gigawatt. So if you're not producing a gigawatt, you're really not playing in the same game. Okay, the cost of solar panels is ridiculously small now because it's decreasing as we change the industrial processes. But part of the reason that it's small is because, one, we offshore the manufacturing to other countries, specifically China. But also, it's only a small fraction of our total energy output comes from solar energy. So if you look at this one, we get 1%. So this is measured in quads, but we happen to be right around 100 quads. But you're getting about 1% of your electricity from solar, 1% of your total energy from solar. So if you wanted this to be 30%, now you need a factor of 30 demand in solar panels, and the cost of solar panels will respond to that kind of incentive. So anyways, everything has its problem. Everything has a trade-off. And so the question is, what trade-offs do you want? And so part of the reason for me doing this series of presentations on nuclear energy was to show the advantages that we have in nuclear energy, especially the advantages we have with the new generation of nuclear energy plants that are ready to come online or that are in the near future able to come online. And also, what are the other things that you can do with nuclear energy once you have it available to you that we weren't able to do with the Generation 2 nuclear reactors that are currently operating. And in particular, we can start replacing some of this industrial demand with nuclear energy. So there we go. That's what I got for you today. Any last questions before we wrap things up? Now, I do need to mention that by the middle of January, I'm going to be switching my stream dates to Wednesday. So I teach on Tuesdays and Thursdays next semester, and so I'm only going to be able to do streams on Wednesdays for the moment because I've got this conference that I'm organizing, and that's taking a lot of time. But so I'll be switching to Wednesday stream at the same time. That will be probably not next week, but the week after. It might be next week. It depends on, I have an interview coming up where we're going to be talking about inflation, cosmic inflation. And so just something to look forward to. I'm looking forward that things are going to be switching to Wednesdays. All right, let's see. What do I think about heat storage? Do I think hydrogen cars will win in the end? So I don't know about hydrogen cars. For one of the things that is useful to remember or useful to consider is that what goes into cars is not necessarily the same thing that has to go into buses. So a lot of cities or like really dense urban environments, you can use different materials for the transportation sector than what you get when you're going in a rural environment or between metropolitan areas. Because with a bus, you can schedule into the rotation, like where the buses go, refueling standards or like the need to refuel. And so, for example, if there was some fuel that was hard to transport, or that maybe it was a little bit more volatile, and so you didn't want to have it just out everywhere on every street corner, you wanted to have it in a place where you can have better safety standards around it, then it would make sense. You could still use it for buses, because then you have a centralized location where all the buses are going to go get refueled. And so transportations within a city can have a different solution than transportation between cities. So that's something to consider. Let's see. What is the issue with transporting electricity? There are a number of issues with transporting electricity, in that you lose stuff in the lines. So you lose power by heating up the power lines. And it's something on the order of 5 to 10%. It depends on how far you have to transmit it, and also depends upon the voltage that you're transmitting. But you lose energy in the transmission process. And so one of the things to consider, if you're spreading out the collection of electricity over a larger area, you have a lot more power lines that are feeding into your trunk line that's going to deliver it to the city. So if you have a single generator, you can produce power on a single line that goes into the high power, like the high voltage lines. But if you're producing it over a square kilometer or a 10 square kilometers or something like that, then you have to feed it. There's a lot more lines at low voltage, and so you're going to have a lot more power loss as you're supplying that electricity in that vicinity. So there's a lot of infrastructure that goes into the more diffuse energy sources and losses associated with it. That's just the nature of the beast. Let's see. Yeah, so the one thing to consider is when you ultimately want to replace all your sources of energy, how much carbon emissions do you get to provide each of these different things? And how do you pay, like, where does it go and how long do they last and what's the overall carbon footprint per kilowatt or kilowatt hour that you're producing? And so a lot of studies don't actually include that. And so they're like, oh, this is totally carbon free, but you have to build it in the first place. And so if you're building it and it takes cement and steel and fertilizer, I mean, it wouldn't take fertilizer, but cement and steel to make your infrastructure, then there's carbon emission associated with that, because the things that you're making, a wind turbine cannot provide the temperatures needed to make the cement that they're built from. Wind turbines can't provide the temperatures needed to make the steel that they're built from. So anyways, there it is. Demon Machines raids just in time for things for us to be done. So we just finished up today, but welcome everybody from Demon Machines stream. So we just finished up a series of discussions about nuclear energy, and that's pretty much where I'm going to leave it off. I'm going to spend some time, the class that I'm teaching next semester is going to be about other sources of energy. Oh, it's going to be nuclear for part of it, but then other sources of energy. And so we'll look into, what's the physics of solar panels and things like that. But I need to read ahead before I can really do that. Anyways. Let's see. Will it be a problem to transport heat out of the regulated area of a nuclear plant into some processing site outside of the plant? So when you do nuclear process heat, let me just draw a real quick picture for that. When you do nuclear process heat, here's your power plant. So you have your reactor in here, and then you just have a heat exchanger, and you send the heat. This material could be just like some kind of regular heating, like some kind of oil or some substance. It could be a molten salt, whatever. This one doesn't have any nuclear, like radioactive materials in it. So you bring it into the reactor, you warm it up in the reactor, and then you send this out. And this can be a totally benign substance. And so you only have to worry about this part of the system, and then you have your, say, paper mill over here, and you just bring the nuclear heat in here and then have another heat exchanger. You blow air across it or whatever it takes to extract the heat from this pipe into your plant, and then you send it back in here and have it warm up again in the reactor. So you only have to control the stuff that's right around the reactor, which would be the stuff right in the reactor. And all of the process heat that comes out doesn't come from reactor materials. It comes from heat that's been exchanged at the side of the power plant. So it will cool down quickly unless it's insulated, right? This can be underground. So you can run these pipes underground, and the thermal conductivity of soil is tiny. You could have it insulated, right? You could have it running underground with a layer of air around it, so that you get even less thermal conductivity. So there are ways to engineer it so that things stay hot over long distances.